In this lesson, we're going to discuss properties of the first derivative, and we're going to begin with increasing and decreasing functions. So let f be a continuous function defined on an open interval from a to b, and x1 and x2 be any 2 points in that interval such that x1 is less than x2. So the ordering there is important to make sure we're defining increasing and decreasing properly. So if the function evaluated at the first x value is less than the function evaluated at the second x value, then f is increasing on the interval from a to b. And if f of x1 is greater than f of x2, so if the function evaluated at the first point is larger than the function evaluated at the second point, then f of x is decreasing on that interval. And lastly, if these two values agree with one another, then the function is constant on that interval. Let's take a look at what this looks like through an app to try and help understand exactly what this means. Here I have 2 points on a function such that p I'm going to make sure is always less than the value of q in terms of their x. So for instance, the x coordinate for p is right now around -3. The x value of q is looking like -2 point, well actually it would be like -1.9 or something like that, but pretty close to -2. The point is that the x value of p is less than the x value of q, and I'm always going to keep that consistent because that was one of the rules in the statement that we just had, is that x1 has to be less than x2. Now, since I have that arranged so that x1 is less than x2, if I look at the y values, the y value associated with p right here is -11 maybe. And the y value associated with q is a little bit above 0, so I'll just say 0.2. It doesn't really matter what that value is. The important thing is that the y value of q is larger than the y value of p. So we have x1 is less than x2, or I could say x of p is less than x of q. And likewise, the way that these two compare, so the function evaluated at each of these points, so the y values, which is the function evaluated at these x values, the y value at point q is larger than the y value at point p, so f of xp is less than f of xq. And if f of xp is less than f of xq, then what the rule said is that this was increasing on that interval. So if we're increasing on that interval, then that's shown through the definition. Now, if I move these points, and first off I want to mention something. If I move q to, say, right here, I have to have this situation occurring at every single point in the interval. So the interval from p to q is not an increasing interval because there's part that's increasing and part that's decreasing. So I need to make sure all the values between p and q end up being such that f of x sub p is less than f sub x sub q, or f of x sub p is greater than f sub x sub q. So we can see here I've moved such that, again, the x value for p is still less than the x value for q. But now when I compare the y values, and again, it doesn't really matter what the y values are, it's just that q is lower. So that means f sub x p is greater than f sub xq. That tells me that I'm on an interval that is decreasing. And if you look at the graph, that makes sense because going from left to right, starting from this point, going all the way over to here, I'm on an interval that is decreasing. So that's what we're seeing through this statement and through this rule. The rule for an interval that's constant is similar, but you don't often have with normal polynomial-based functions constant intervals. You generally have intervals that are either increasing or decreasing. Now let's connect these ideas back to the concept of a derivative. All right, so suppose that we're on an interval that's increasing. So we would know that for all x1 and x2 in that interval, f of x1 is going to be less than f of x2. That's by definition what an increasing interval means. Now, since x1 and x2 are distinct points, and f of x1 and f of x2 are their corresponding y values, we can calculate a slope between them. These are just 2 points on a plane, and you can always calculate the slope between any 2 points. Slope, by definition, is f of x2 minus f of x1 divided by x2 minus x1. Okay? Now, if one thing that I know about x1 and x2 is that x1 is always going to be less than x2. That was just through our definition of an increasing interval. This has to be the case, so that we're reading the graph from left to right, because if we go in the other order, increasing and decreasing concepts flip. Now, suppose I was to subtract x1 from both sides. What I would end up with is 0 is less than x2 minus x1. What that means, if 0 is less than a number, that number is positive. So x2 minus x1 is 0, is greater than 0. So this means the same thing as x2 minus x1 is greater than 0. Okay? Now, we also know from this statement right here that f of x1 is less than f of x2. If I subtract f of x1 from both sides, what that tells me is 0 is less than f of x2 minus f of x1. And if 0 is less than a number, that means that number is positive. So another way of rearranging this and thinking about it is f of x2 minus f of x1 is greater than 0. Maybe that makes more sense to see it that way. So if I'm on an increasing interval, what this means is the numerator of this fraction is greater than 0, and the denominator is greater than 0. So these are all positive numbers divided by positive numbers. When you take a positive divided by a positive, that results in a positive number. So the result is always a positive slope. And that's the important thing here, is when you are on an increasing interval, the secant lines always result in a positive slope. If you're on a decreasing interval, the secant lines through a similar argument can be shown to always have a negative slope. So it's going to follow that the slope of a tangent line on an increasing interval is positive, because we're using secant lines to approximate the value of tangent lines. So as that approximation gets better and better, these things are going to agree with one another, and therefore these properties are going to agree with one another. So if we know that the slope of a secant line on an increasing interval is positive, we know that the tangent line at a particular point is also going to be positive. And since the derivative of a function can provide the slope of a tangent line at any point of a function, what we can deduce from this is if the derivative is greater than 0 on an interval, then f is increasing on that interval. Or if the derivative of a function is less than 0 at a point on an interval, then the function is decreasing on that interval. Likewise, if the derivative is 0, then that tells us that the function is constant on that interval. Coming back to a visual aid to make sure you fully understand how this is working. I have a function with 2 points that are on an increasing interval. And you should be able to tell that this is on an increasing interval because the function is getting larger in y values, going from negative to positive. So for x values that are increasing, the y values are increasing as well. Now, if I calculate a secant line between these 2 points, then the secant line, its slope is positive. So you should know the difference between a positively sloped line and a negatively sloped line. This is a line that is positively sloped. And if I move these points P and Q to any place within this interval where my function is increasing, I have a positively sloped line. But if I move these points into an interval that is decreasing, then I end up with the slope of a line that is negatively sloped. And likewise, in terms of derivatives, if I'm looking at derivatives at a point in an interval that is increasing, the derivative is positively sloped. If I'm in an interval that is decreasing, the derivative is negatively sloped. And that relationship holds through all types of functions throughout all of calculus. And that's one of the most important properties of the derivative, to learn where a function is increasing and decreasing. Let's take a look at an example where we try to determine the intervals where a function is increasing or decreasing. Now, when it comes to changing between increasing and decreasing, we have to come to certain points where these changes occur. And that's always going to happen at critical numbers. So the point where relative extrema could possibly occur. So the first thing that we need to do in order to determine intervals of where a function is increasing or decreasing is locate critical numbers. So let's start there. Now the critical numbers can occur where the first derivative is equal to 0 or the first derivative is undefined. Now, most of the time our functions are nice and behaved and we don't have to worry about undefined points, but sometimes they're not. So don't forget that part, but a lot of your problems will just be finding the first derivative and setting that first derivative equal to 0. The first derivative here, it would be 2/3 of 3x squared minus 2x. These 3's cancel, and I'm left with 2x squared minus 2x, which can be factored, and leaves me with x minus 1. And that right there, if I set that equal to 0, so if I set 2x times x minus 1 equal to 0, I get the solutions of x equals 0 and x equals 1. So those are my critical numbers. That's where we're going to have horizontal tangent lines. Okay, so it's in between these values where the tangent lines would not be horizontal. They'd either be positive or they would be negative. So we'd have to determine how that's occurring. One way of determining that is to take these critical numbers and place them on a number line. And we use test values within these intervals to see if the function is increasing or decreasing. So for instance, the function is either entirely increasing or entirely decreasing from negative infinity up to 0. So I need to pick some value between negative infinity and 0. So how about negative 1? That seems like the smallest number that's still on that interval. And if I see what's happening to my function at negative 1, then I know what's happening at negative 2, negative 3, negative 4, and all other values in that interval. So they're all either increasing or all decreasing, one of the two. So to find out, I need to come over and do a test and just find out what the first derivative evaluated at negative 1 is. So the first derivative is 2 times the input value times the input value minus 1. So negative 1 minus 1. So this is 2 times negative 1. I'll just make that negative 2. So negative 2 times negative 2 is positive 4. It doesn't really matter so much exactly what that number is. It just matters if it's positive or negative. So the first derivative is positive, which means I am entirely increasing on this interval. Sometimes instructors will put a positive there. You can write increasing so that you know that that's what that means. It doesn't really make a whole lot of difference. All right, so move on to the next interval. You have to have some number within that interval and pick the smallest number that fits. Here, unfortunately, we do have to do a fraction, but that's generally not too bad because we don't really need to evaluate this derivative and get a final answer here. We just need to know if it's going to be positive or negative. So let's see, 2 times a half times 1/2 minus 1. Well, 2 times a half is 1. 1/2 minus 1, it's negative 1/2. But even if I didn't take the time to figure out that it was negative 1/2, the result is a positive number times a negative number. So the result is going to be negative, which means I'm entirely decreasing on this interval. And then finally, I need something on the interval from 1 to infinity. Generally, the smallest integer that will work is probably your best choice. So this would be 2 times 2 times 2 minus 1, or 4 times 1, which is positive 4. So everything on this interval is positive, which means this interval, everything is entirely increasing. So if I want to answer where this function is increasing and decreasing, I can now do that. I've never even looked at the graph, and I can already do that. So this function is increasing on the interval from negative infinity up to 0. We don't include the endpoints here for increasing and decreasing, so don't worry about open bracket or parentheses versus brackets here. You can always use parentheses for increasing and decreasing. All right, and then it's increasing again from 1 to positive infinity. But it's decreasing on the interval from 0 to 1. And if we take a look at the graph of this, that's going to mesh up with our results here. So here's the graph, and what we can see is that the function does have horizontal asymptote here and here, which is at 0 and 1, just as we expected. The function is increasing, so it's getting larger in value up to this point at 0. Then the function turns and it starts decreasing in value. So it's decreasing all the way to the point x equals 1, and then it turns and it starts increasing again. So the y values are getting larger. So where we have these relative extrema, that's the potential places where we could change from increasing to decreasing. And that's exactly what we learned in our analysis, but we didn't use the graph at all until the very end just to make sure our results were correct. And also notice that if we know if our function is increasing or decreasing around a relative extrema, we actually have a means of determining if those relative extrema are minimums or maximums. Because if we go from an interval that is increasing and then switches and starts decreasing, it's going to go from increasing to a point and then start decreasing. That point has to be a maximum. And then if we are decreasing, come to an extrema, and then we start increasing, well, that point has to be a minimum. And that's what's known as the first derivative test. This states that we can label a critical number as a relative minimum or relative maximum, or neither, based on whether the function is increasing or decreasing in the neighborhood surrounding that critical number. And if c is a critical number of the function f, then if f changes from increasing to decreasing, then f of c is a relative maximum. If f changes from decreasing to increasing, then f is a relative minimum. And if it does not change, then it's neither a minimum or a maximum. Where we identify any points of extrema for a function. Now this is asking us to come up with the critical numbers and use the first derivative test in order to identify if those critical numbers are relative minimums, relative maximums, or neither. So it begins finding those critical numbers. The critical numbers you should get pretty comfortable with the fact that critical numbers are found by taking the first derivative, setting it to 0, or we're finding the first derivative is undefined. Now, with polynomial functions, we don't have undefined values to worry about, so effectively we need to get the derivative, which in this case is 4x cubed minus 6x. And there's a common factor of 6x squared. Apologize for that. There's a common factor of 2x squared between each of these terms. I'm going to factor that out. That's going to leave me 2x minus 3 on the inside of these parentheses. Now, if I set each of these factors to 0, I do get x equals 0 for the term 2x squared. But if you're uncertain exactly what 2x minus 3, what its 0 will be, just take the factor and set it to 0, and when you solve it, it will very quickly determine for you that it is positive 3/2. So these are my two critical numbers. Now, to find out if these critical numbers are relative minimums, relative maximums, or neither, we need to put those critical numbers on a number line. So 0 and 3/2. And it goes from negative infinity all the way to positive infinity. Now on each of these intervals, my function is either entirely increasing or entirely decreasing. So for instance, if I determine what my function is doing at -1, I'll know in this entire interval what it's doing. If I see what my function is doing at +1, same result. 3/2 is it is 1.5. So if I use x equals 2, then that's a value in that last interval. So I just need to test and find out if my function is increasing or decreasing in each of those intervals. And to find out if it's increasing or decreasing, what I do is plug it into the first derivative, because the first derivative will tell me if my function is increasing or decreasing. Okay, so this would be 2 times negative 1 squared times 2 times negative 1, which is negative 2 minus 3. So this is 2 times negative 5, which is negative 10, but again, it doesn't so much matter that it's negative 10, more so than it is a negative number. So my function is decreasing on this interval. The first derivative evaluated at positive 1 would be 2 times 1 squared times 1 minus, or 2 times 1 minus 3, which would be 2 minus 3, which is 2 times negative 1, which is negative 2. Again, it matters more that it's negative than anything else. So it's decreasing on that interval. And lastly, my derivative is at 2, it is 2 times 2 squared times 2 times 2 minus 3. So 2 squared times 2 is 8. 2 times 2 is 4. 4 minus 3 is 1. The result over here is positive. So we are increasing on this interval. So what we can determine is that at x equals 0, I go from an interval that is decreasing, so it's getting smaller in value, and I reach a relative extrema, and then it continues decreasing. So what happens there is we don't actually have a minimum or a maximum. So this is neither a minimum or a maximum. It's a point of interest, but it's not a minimum or a maximum. Sometimes the questions are worded so that they want the y values instead of the x, or even sometimes they want the entire point. So if they want the entire point, you need to take your x value and plug it into your function to get the corresponding y. In this case, that would be the point 0, 0. So you may have to answer the point 0, 0 is neither a minimum or maximum. Now at x equals 3/2, let's see what's happening there. So we're on an interval that is decreasing. We hit a relative extrema, but then it turns and it starts to increase. So there we had a minimum value. So we have a relative minimum at that point. And again, if the question is asking in such a way that it wants the coordinate for that particular point, which sometimes it is, then you just need to plug back into the original function to figure out where that coordinate is actually located. In this case, if you plug it into your calculator, you get negative 1.6875. So the coordinate pair would be 3/2 and negative 1.6875, or if you wanted as a fraction, you could have solved it and gotten negative 27/16. But if you're graphing it, a lot of times it's the decimal approximation that you need for the graph. Just be careful. Sometimes your instructor will ask for exact answers only. Sometimes they'll ask for approximations. The decimal value is the approximation. The fraction is the exact value. So be careful as to what your instructor requests. Now, if we look at this function just to verify that everything's working out as expected, here's a graph of it, and we can see at the point 0, 0, which is where p is sitting at this time, and that point we were decreasing up to that point, and then we were decreasing again after that point. So that's why we had neither a minimum or a maximum. Then at 1.5, we have this next relative extrema, and we're on an interval that's already decreasing, but then it switched to increasing after that, which gave me a minimum value. So that's why we have a relative minimum. So everything works out with respect to the graph. Determine the location of any relative extrema for the function y equals x to the 2/3 power minus 2. Okay, to find relative extrema, which which are minimums, maximums, or neither, first thing we need to do is locate critical numbers. So the critical numbers are where the first derivative is 0 or undefined. So the first derivative is going to be y prime equals 2/3 x to the negative 1/3 power, and that's going to be our derivative because the minus 2 goes to 0. Now we can rewrite this so that we get, just making the exponent positive, 3 times the cube root of x. Now, if I set this equal to 0, I'm not going to be able to solve for anything, because if I set 0 equal to this particular function, then the first thing we'll want to do is get the cube root of x out of the denominator. But if we try to do that, the only way we can is to multiply both sides by that denominator. And it does get out of the denominator on the right-hand side, but 0 times anything is still 0. And the result 0 equals 2 just doesn't give us any particular solutions. So we don't get any critical numbers through where the derivative is 0, but the derivative is undefined at x equals 0 because we get division by 0. If we try and evaluate y prime of 0, it's 2 over 3 times the cube root of 0, which is 0, or 2 divided by 0, so it's undefined. That's a point of interest as well. Okay? Which means we need to develop our potential places where we could be increasing or decreasing around that point of interest. So I have two intervals, negative infinity to 0 and 0 to infinity, and I need to test those. So my test values, I could use -1 and +1. Alright, so if I try to evaluate the derivative at -1, it's 2 over 3 times the cube root of -1. And you might think that this would be a problematic number because if you try and take the square root of a negative, that's an issue. But this is okay. You can do the square root of the cube root of a negative. So this becomes 2 over -3, which is a negative number. So that means I am entirely decreasing on this interval. If I plug in +1, 2 over 3 times the cube root of +1. I don't know why that 3 is so tiny. But then what I get is just 2/3, which is a positive number. So my function is increasing on that interval. So I'm going from an interval that is decreasing to an interval that is increasing. That means I have a minimum value there. And if we look at the graph, that's exactly what's happening. We have this point right here, and it is at 0, -2, because you can calculate the y coordinate just by plugging in 0 to the original function. So that would be, if you plug in 0, 0 to the 2/3 is 0, then -2. So 0, -2. This is we said it was a relative minimum. And that's exactly what we're seeing over here, because my function is decreasing from left to right, and then it turns and it starts increasing from left to right around that point. But the derivative is undefined at that particular point. So you do have to keep in mind that you have to watch out for points where the derivative could be undefined as well as 0. These are both places for critical numbers. Now let's take a look at some graphs of derivatives. So when you compare the graph of a function to its derivative, it's not always entirely obvious as to why the graph of the derivative looks the way it does. However, there's a few key features that we can always rely on. One, if the derivative is positive, so if the graph of the derivative is above the x-axis, then that means the original function is increasing. If the derivative is negative, then the original function is decreasing. If the derivative is 0, then the original function is either on an interval that's constant, or it has a potential maximum or minimum, which is probably more likely the case because we're not generally looking at constant intervals. And another thing we can count on, if you consider the power rule for differentiation, the derivative of a polynomial is usually another polynomial whose degree has been reduced by 1. So a quartic polynomial has a derivative that's a cubic polynomial has a derivative that's a quadratic has a derivative that's a linear, and so forth. So you can sort of deduce what the graph is going to look like of polynomial functions with that respect. But suppose we want to sketch a graph of a derivative. So if we're given a function, how can we put these properties together to sort of predict what the graph of the derivative would look like? So let's try it together. Here's a graph, and this particular graph, I want to sketch its derivative. So I'm going to go ahead and just label this graph as f of x. It's the original function. Now, a couple of things that we can rely on. First is wherever this graph has minimums or maximums, the derivative is 0. So at this point right here, the graph of the derivative is going to be 0. So it's going to cross the x-axis there. And at this point, the derivative is going to cross the x-axis there. Anytime we have minimums or maximums, that's going to be the case. Well, that's 3 points out of an infinite number. So it's a start, but it's clearly not where we need to end this process. Other things that we can count on is wherever a function is increasing, the derivative has to be positive. So in this interval right here, the derivative is going to have to be greater than 0. And if you're greater than 0, that means that you are x-axis. So the graph of my derivative has to be above the x-axis on this interval. So I'm just going to draw a graph, and it needs to be bending. It can't just be a straight line here. But I'm just going to draw a sketch of a graph that's above the x-axis. There we go. Now, on this next interval, the original function here is decreasing in value. And if the original function is decreasing, then my derivative has to be less than 0. So it has to be negative on this interval. So if I'm negative on this interval, I just need to go below the x-axis, and I come up to this point because I have to reach that 0 again. So I know that the derivative reaches a minimum and then kind of comes up. Alright, on the next interval, my function is increasing. If my function is increasing, my derivative is greater than 0. So what I'm going to do is draw a part of a function that is greater than 0, but it has to come back to this point over here because I know that's a point on my derivatives graph. And lastly, the function is decreasing over here, so that means my derivative has to be less than 0. So it needs to be below the x-axis, and there's no other points for it to come back to the x-axis again, so it's going to descend down to infinity. So this red graph is a pretty decent sketch of what my derivative would look like. Now, it's potential that the derivative of this graph might have higher and lower minimums and maximums. That's okay. We're not determining where those points are right now. We're just seeing where the graph would be positive, where it would be negative. And you can actually do this thing in the opposite order as well. If I give you the graph of a derivative, you could produce the potential function by locating where the minimums and maximums of the functions would be. and where the function would be increasing or decreasing. Now, let's take a look at an applet to see how the actual values of a derivative relate to a given function. Because if you want to see exactly how that works out, we need to have aid in the calculation here. Okay, so what you're looking at here, we have the graph of the function x minus 1 quantity squared minus 2. So it's just a parabola. It has a single relative minimum value, and that graph is in blue. The derivative of this graph is in green. So I've already calculated the derivative and graphed that function for you. Now, point P is on the original graph, and then there's another point that is on the derivative itself. And what I want you to see is how these points on P, or how these points at P on the original function get mapped to the derivative. The first point we already know. So whenever the function itself has a minimum or a maximum, the derivative is 0. You can see that's the case. My tangent line has a slope of 0, and everything is at 0. Now, if I move point P to, say, right here. Actually, I'll go a little bit further. I'll go to about 1.5. All right, so I'm at about 1.5. The slope of the function at P is 1.06. So it's being measured for us, and we're being told what the slope of this tangent line is. So basically, this is kind of like a delta x, and this is a delta y, but it's just telling us what that delta y is. So we're looking at the slope of the tangent line here. If we take that slope of this tangent line and move it over here and produce a point above the x-axis, then what we get is the location of the derivative. So if we move this point around, what you'll notice is as the derivative increases, so as the slope increases, the location of where that exists on the derivative's graph gets higher and higher. And it's doing so in a linear fashion. So that's why the graph of this derivative is a line. If we go into an interval that is decreasing, so if I go past this 0, now I'm on an interval that's decreasing. So the slope of this line is now measured as a negative slope. So the derivative is a negative value. So really, it's not so much always important what the value of the derivative is. Sometimes that's important. Oftentimes it's whether it's positive or negative is really what we care about, because what we know is that derivative, if it's negative, and if it's negative up to a particular point, and at that point it switches and becomes positive, then we know that our original graph has reached a minimum or a maximum. And in fact, it would be a minimum at that point if we go from decreasing to increasing. So that's how the graph of a derivative is determined. So let's go back to other applications. All right. Let's talk about linear approximations. So we've discussed previously how the derivative linearizes a curve. It gives us the slope of the best fit line that would match the slope of the curve at a particular point. So it linearizes the curve. We can use this property to make approximations for functions using a derivative around small increments of known values. And that's what's known as linear approximations. So for instance, let's use an example function, negative 1/2 x squared plus 6. The derivative of this function, if you just use the power rule, you get f prime of x is negative x. Now, we'll choose any point along the curve, and for no particular reason, I've just picked positive 2. So, the function evaluated at positive 2 is negative 1/2 times 2 squared plus 6, which would be, so 2 squared is 4, 4 divided by 2 is 2, so negative 2 plus 6, which is 4. So this function evaluates to 4. Now, if I pick another point that's close to 2 and evaluate it, and 2.01 is going to be a little bit more difficult to do in my head, so I think I'll grab the calculator to evaluate this. So let's see, it would be negative 0.5, so the negative 1/2, times 2.01 squared and plus 6. So 3.97995. So 3.97995. If you'll notice, the function didn't decrease. It did decrease, but it didn't decrease very much. And how much that decreases can actually be predicted by the use of the derivative. And that's the whole objective of the linear approximation. So, if we work this through and look at the details, the change in our x value was, we went from 2 to 2.01. So 2.01 minus 2 is 0.01. We had 1/100th of a change, so 0.01. The corresponding change in the y values was 3.97995 minus 4, which I'll get the calculator for that. So just take that minus 4. Negative 0.02005. I don't know why I put past tense there. Those values are that, not was that. Now, if we go back to the definition of a derivative, we can establish a rule about approximations. So, just for a second, we're going to go back to the statement f prime of x is the limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. So this is just the original definition of a derivative that we came up with so long ago. Now, this right here we can change into an approximation if we take away the limit. So we can say the first derivative is approximately f of x plus delta x minus f of x all over delta x. So without the limit, it's only an approximation. It's kind of like the difference between a secant line and a tangent line, which it is in fact exactly what's happening. Now, this statement we could say f prime of x is approximately the change in y over the change in x. And if you'll notice, up here I've calculated change in x and the change in y. Okay? So, just if you want to see it, if I take the change in y divided by the change in x, that gives me an approximation to the derivative at that point. If you'll remember the derivative, it was negative x. So the derivative at 2 is negative 2. So this point is an approximation to the derivative. It's not exactly, but it is close to it. And what we can say then is, if I multiply delta x to both sides, I can say delta y is approximately f prime of x times delta x. And this is our rule for linear approximations, right? And it tells us how this all fits together. So if we calculate the derivative at 2, and just so you recall, the derivative for this function was negative x, so that's negative 2. Delta x was 0.01. Then delta y is approximately f prime at 2 times 0.01, or 2 times 0.01, which is 0.02. So we've basically come up with a means of using the derivative to approximate the amount of change that would have occurred. And sorry, f prime of 2 was negative, so this is negative 2, and that's negative 0.2. So the change was decreasing. So we've come up with a way of approximating this change using the derivative. So this is a way that we can use a derivative. So you might be wondering how this could be useful. And the way that this could be useful is sometimes when you're modeling using mathematics in the real world, you can find out how things are changing, but you can't exactly determine where pieces are. And if you can determine how they're changing, you can use that to predict where they are from those increments. So for instance, you might have a measurement of how much water passes through a pipe per unit time. That's going to be a rate of change. You might not be able to measure how much water is exactly at a point, but you can see how it changes. And this could be a way of predicting how much water is going through. Or if you're comparing predator-prey models, if you can see how many predators change based off of the number of prey that exist, you can see how those values change with respect to one another. You can make predictions on how many of those items actually exist. So sometimes you can get a derivative, but you can't get the original function, and that's why you need things like this. Now, let's take a look at an example where this could be utilized. And we're not using predator-prey models or anything fun like that, but just here's a simple example. So we know that the cube root of 27 is 3, right? And pretend like we don't have a calculator that can do a cube root for us. Okay, and we want to determine what the cube root of 28 is. It wouldn't be all that crazy, given us, a small number of years from now in the past, that we wouldn't have a calculator that could do that sort of thing. So we might need to be able to make predictions as to what these values are given known. So let's see what we can do. Let's see if we can take the fact that the cube root of 27 is 3 and determine an approximation as to what the cube root of 28 is. Now, to do that, we need to define a function for the cube root. So we'll say, we need to define a function f of x, which is the cube root of x. So we'll make a function for the cube root. The derivative of that function is going to be 1/3 x to the negative 2/3 power, or 1/3 times the cube root of x squared. Okay? Now, the distance between these points from 27 to 28, so that's the change in my x value. So 28 minus 27 is 1. So my delta x is 1. My delta y, so the change in the y values, is going to be, well, I should be careful and say this is approximately the derivative evaluated at the original point, 27, times delta x. So let's take a look. Let's see what happens. So we know that the derivative evaluated at 27, the way we can do that, actually I'll come off to the side and do it. So f prime evaluated at 27 would be 1 over 3. Now instead of doing 27 squared and then the cube root, you can actually do the cube root of 27 first and then square it. That's going to be a little easier because it makes the number smaller. The cube root of 27 is 3. 3 squared is 9. 9 times 3 is 27. So this is 1/27 times delta x, which is 1. So that means the change in y is approximately 1/27. And the change in y is the function evaluated at x plus delta x minus f of x, which in this case would be f of 28 minus f of 27. And what that tells me is that I'll set it equal to delta y. What that tells me is that f of 28 would be equal to f of 27 plus that change in y. But it also means that this would be approximately f of 27 plus this approximate change in delta y, which I came up with as 1/27. So this would be 3 plus 1/27, and 3 plus 1/27, just so we can see a decimal value to compare with. 3 plus 1/27 is 3.037. And if I do the cube root, let's see, I gotta do math, and then cube root of 28, let's see how we did. It comes out to 3.03658, which if you round to 3 decimal places, that's 3.037. So it's correct to 3 decimal places, this approximation. But we didn't need a calculator for anything until the very end, and we could have actually used long division to come up with 1/27. So you can use these linear approximations to make predictions about unknown values of your function. Now, last thing I want to discuss is a definition of what's called a differential. So if y equals f of x is a function that's differentiable in an open interval containing x, then the differential of y is dy equals f prime of x dx. This tells us how changes in y occur with respect to changes in x, and those occur through the derivative. Now, if you'll notice, this is very similar to our rule for approximations. Effectively, if you take delta y is approximately f prime of x times delta x, and you go through the limiting process, you end up with dy equals f prime of x dx. So it's the same rule, just through approximations, or through the limit process. So let's find the differential of y equals x squared plus 2x minus 1. So the differential of y is going to be the f prime of x, which in this case we will call y prime. The derivative here is just 2x plus 2. So 2x plus 2 goes here, then times dx. It's really just a different form of the derivative. So as opposed to saying dy dx equals 2x plus 2, we say dy equals 2x plus 2 times dx. This will become important as we get later into the class, but for now, just understand if you want a differential, you are defining, in this case, dy in terms of f prime of x times dx.